the end of the classical web. What if the very backbone of the internet could be rendered obsolete by the laws of physics themselves? Today's global networks route bits, zeros and ones, through cables, satellites and fiber optics. But they all remain vulnerable to eavesdropping and cyber attacks. Imagine exchanging messages that cannot be intercepted or copied without leaving a trace. Is it even possible to build a truly unhackable network? Not through stronger firewalls, but by harnessing quantum phenomena. Quantum bits on the move. Classical data travels in packets. Quantum data travels in qubits. Delicate superpositions of 0 and 1 carried by photons. These single photon qubits traverse fiber or air. But any disturbance collapses their state, alerting both sender and receiver to tampering. Picture a single photon as a tiny courier in a cobalt-lit hallway. If anyone tries to inspect its contents, the courier vanishes. How do we generate, shape and guide these fragile qubits across continents without destroying their quantum state? Entanglement, spooky action for communication. Einstein derided entanglement as spooky action at a distance. Yet it's the cornerstone of quantum networking. When two photons become entangled, measuring one instantly determines the state of the other, even if they're oceans apart. This allows quantum teleportation, transferring an unknown qubit state from sender to receiver without sending the particle itself. Could entanglement ultimately let us transmit information faster than light? Not quite. Quantum mechanics still obeys relativity, but it does open a door to instantaneous correlations that classical physics cannot emulate. Bridging continents, repeaters and satellites, qubits lose coherence quickly, limiting fiber-based quantum links to a few hundred kilometers. To span continents, we need quantum repeaters, devices that entangle qubits over short hops and swap entanglement to extend the link. Alternatively, satellites can beam entangled photons between ground stations across thousands of kilometers. China's Mikius satellite proved this in 2017, linking Vienna and Beijing via spaceborne entanglement. What engineering marvels! Cryogenic memories, precision optics, orbital tracking. Must we perfect to scale these links into a global quantum backbone? Securing the network. Unhackable cryptography. Quantum key distribution, QKD, leverages the no-cloning theorem. Qubits cannot be perfectly copied. Any interception attempt introduces detectable errors. With QKD, two parties can generate symmetric keys in full view of eavesdroppers, then immediately discard the compromised qubits. If you're excited by the promise of encryption that betrays every prying eye, hit like and subscribe. Because with quantum networks, the act of eavesdropping becomes the alarm bell itself. Vision for tomorrow, from lab to global scale. Quantum networks remain nascent. Laboratory testbeds connect tens of nodes. Real-world trials link major cities. Companies and governments worldwide invest billions to build metro-scale networks by 2030 and continental backbones by 2040. As we edge toward a future where the internet's security is guaranteed by nature's laws, what new applications will emerge? Will quantum-secure voting systems redefine democracy? Could global science collaborations share data instantaneously and tamper-proof? The quantum internet challenges us to rethink trust, security, and connection itself. What will you build when the web of tomorrow arrives?